What the heck is up, guys? It's Jacob here, and in this video we're going to be taking a look at the Triac. Now, in my last video I did a video on SCRs, and I mentioned that they were very similar to Triacs, and we'll take a look at that in this video. They're very similar. In fact, you can actually build a Triac out of SCRs. A Triac is really just two silicon-controlled rectifiers. So we're not going to go into too much depth as to how the actual current flows through the PN junctions or anything in this, because really it is the same as the SCR. So if you guys are really interested in how the current really flows through the junctions at different parts of the cycles, look at the SCR video and you'll see how that works. But yeah, so for this video we're just really going to focus on a little bit higher level. We're just going to look at the Triac itself as composed of two SCRs. Alright guys, so to start, here's the actual symbol for a Triac. So it is a 3-terminal device, and it has a lot of the same properties as a diac, or not a diac, I'm sorry, a SCR. So the Triac is really just like an SCR. If you watch my other video, you'll see all the properties as far as how it behaves with AC. These guys perform just as well as AC. So they're very similar to that SCR. Really the only difference is it will work with full wave. If you watch my video on SCRs, you'll know that SCRs can pretty much control AC power. You can use them as an AC switch, a solid state AC switch, or you can use them as actual phase controllers, so you can cut, you can kind of it can act as a switch which will cut in at a very specific point of your actual AC sine wave, and that's what we call phase control. So this guy will do full wave phase control, so it'll do your positive and negative half of the cycle, and we'll look at that in a little bit more detail here in a minute. But so here's the terminals. So there's A1 and A2 is sometimes what they're called. This is just anode 1, anode 2. So you can see here there's two SCRs. We'll look at that in a second. But so it's not really polarized like the SCR. The SCR has an anode and a cathode terminal on it, and then it has a gate terminal. So it does matter what way you hook up an SCR. In this case, since there's two SCRs back to back, it doesn't really matter. You'll have an anode pin here and an anode pin here. And they're also commonly called main terminal 1 or main terminal 2. Again, it's the same thing. It doesn't really matter what way current flows. It's going to flow both ways anyways if it's used in an AC application, which is typically what these guys are used for. And then there's your gate pin right here. So if we look at it over here, this is how an actual Triac is typically composed of. It's basically two SCRs. We can actually build a Triac out of two SCRs. A few disclaimers I just want to say. Triacs are a little bit more complicated as far as their gate firing circuitry. They operate in what we can think of as quadrants. We'll look at that in a few minutes. It's a little bit more advanced, but they operate. You fire these things in the quadrants of your AC sine wave. We'll look at that. But the actual gate current to drive a Triac is a little bit more than an SCR to a comparative SCR. So if you had a Triac and an SCR with comparative current and voltage ratings, you would still have to drive the gate of that Triac with a little bit more current. And also it has different sensitivities depending on what part of the actual sine wave you're on. But anyway, so here we have an SCR. So if we just ignore this over here, really all we have is an SCR, right? So it's the anode, here's your cathode, and here's your gate. And so when you could imagine if you're feeding AC into here, right? On the positive half of your sine wave, this Triac is going to be forward biased. So it's going to be forward biased all the way up to this point right here, right? And so if you're feeding your wave in here and your load is going through here to this side on this terminal, on this half of your wave, this Triac is going to be forward biased. And if you have a positive voltage on your gate relative to your cathode, current will flow through and you'll have your positive half of your wave will make it out here, right? Just like that. Not too complex. So we looked at that in the SCR video. But the difference is now we have this other SCR here, and it is flipped the exact opposite way. So it'll be forward biased, I guess you can think of it. It is forward biased. It's a little bit harder to think about. It's kind of backwards on this negative half of the wave because you're feeding a negative voltage in, right? And this side will actually be more positive relative to this side. Your anode will be more positive relative to your cathode. And this guy will be forward biased, and that'll let your other half of your sine wave through. And so as long as you have a negative voltage on your gate in this half of the cycle, it'll fire this SCR, and you can get full wave switching. And you can use this as a solid state switch to actually turn on. You can use it just like a relay if you want to get the full AC wave through, or you can look at how we did it in that other video, where you can really control this gate in a very precise manner with some resistors and diodes and things like that. Or you could actually hook this gate up through a Triac driver and hook it up to something like a microcontroller where you can monitor the wave and fire it at very specific points. And so basically you can do the same thing that we looked at in our previous video. We actually did that on the oscilloscope where you can do phase control, and I showed you guys that if we use, I showed you exactly a circuit and how it was hooked up and kind of how that worked. If you put a resistor on here, your Triac or your SCR will fire at a very specific part of this wave, and you can use that to do what's called phase control. That's a very simple analog way of doing it. You can also have like a microcontroller or something that's analyzing this waveform and looking for where the zeros cross, where it actually crosses through zero, and you can have that, a microcontroller or something, go to a Triac driver and fire this Triac at very specific points in this waveform. And basically you'll get something that looks like this, where you can, instead of getting a full sine wave out, you can use that like a switch like that and get the full sine wave out. But you can also hold off and not fire this, not actually activate the Triac or trigger it until this part of the wave, or any part of the wave really, and you're cutting off a fraction of your top and your negative half of your sine wave. And that's basically limiting the amount of power or current, the amount of time that current is flowing through your load, and that allows you to do things like you can control lights, like incandescent lights, or motor. It's used often in motor controllers or in like resistive heating elements if you want to do a resistive heating control, so you want to limit the amount of power that goes through your heater, things like that. Alright guys, so now we're going to look at just a IV curve for a Triac. It's very similar to a Diac, and in fact I just left the same graph up here from the Diac and just fixed a few things over here so that it would match what a Triac looks like. So if you guys watch my Diac video, you'll know, or not, I keep wanting to say Diac because it sounds like half of a Triac kind of, but a Diac is different. We'll do a Diac video. It is not a Diac, I mean an SCR. So it's very similar to an SCR curve. In fact, it's identical on this side, and then this side was a little bit different. It just didn't have that, you weren't able to actually activate it in the negative half of the cycle. The only time it would actually conduct in the negative half of the cycle is if you reach the breakover voltage. But so this is a Triac. It's really the same as the SCR curve. So let's go through it real quick. So in the forward blocking region, I explain this a lot more in my SCR video too, so watch that. Definitely watch these two because they're very similar, and I explain a lot more things in that video in greater detail. But anyways, so this is your forward blocking region right here. So basically on the positive half of your sine wave, if this will block the actual current flow, it will not conduct unless you go over the forward blocking or the forward blocking voltage or the breakover voltage, which is not really recommended. I said that in my SCR video as well. Typically they don't want you to even go anywhere near this, and this can range anywhere from 25 volts up to, I think there's like 600 or 800 volt Triacs. They go way up there, so they're very big. I think there's probably even higher power Triacs that go up to like 12 or maybe even a couple kilovolts. That's kind of high, but they go way up there. These are high power devices. Typically they're used in more industrial applications. So it will not conduct. It has a forward blocking region, right? Kind of like a diode, and it won't activate unless you reach this forward breakover voltage. That's one condition that will push it into the conducting region. Not ideal. You don't want to use that. You typically don't rely on that in your design. Or if you activate it from the gate. So if you trigger the device from the gate and you have that gate current that's needed to actually put it into the conducting region, it will then shoot over to the conducting region, and you can see that your current goes way up in that region. So this happens almost instantaneously. It takes just a couple of microseconds to switch from the forward blocking region to the conducting region, and it works just like an SCR in the fact that it latches. So once you're in the conducting region, it will stay in that conducting region, and it'll keep conducting until your current falls below the actual holding current. So it'll hit the latching current and it'll latch, and then once it goes there, it'll stay latched, and it'll keep conducting. It'll stay in this conducting region until you fall below your holding current and your gate is no longer triggered. So those two conditions have to be true as well. And same as the SCR, these two, the latching current and the holding current, are typically the same. Not always, but they're usually very close, so they're about the same. And This same exact thing happens in the negative half of the cycle. It's just basically a mirror image, but for the negative half of the cycle. So you have a reverse blocking region as well, and it will not actually conduct until you hit the, I didn't actually label this, I should have labeled that, but the reverse breakover voltage. So this is if you're in the negative half of your cycle, right? And if you reach that extreme negative voltage, that reverse blocking voltage, the maximum reverse blocking voltage, it'll shoot into the conducting region here and become conductive. But typically, again, that's not used. You'll just have your gate trigger, and you'll have it actually triggers with a negative voltage on this half of the cycle. So you'll push a negative voltage into your gate, it'll trigger it, and it'll shoot, boom, into the conducting region. It'll latch with your latching current, and it'll hold there until the current falls below the holding current for a significant amount of time. It still takes it takes a certain amount of time to actually unlatch. So you have to fall below your holding current for, like I said, it's on the order of tens of microseconds. So 20, 30 microseconds, somewhere around there. So it does have to fall below that holding current for a certain amount of time before the actual Triac will unlatch, and it'll fall down back into these blocking regions here. So again, these are used a lot in AC control. That's what they're mainly used for. You don't see them used, there's really no purpose of using this in a DC controller. SCRs maybe, they're kind of useful on DC circuits, but this is really just strictly an AC device. I mean, you could use it on AC or on DC, but there's really no purpose in it. If you want a latching device in direct current, you're probably going to use an SCR. This is really just an AC specific device. So typically your holding current, because you're constantly, your current's constantly changing in an AC waveform, it's going up and then it hits zero at some point, right? And let's say your holding current is right here and right here. So here's your positive holding current, here's your negative holding current. And as long as the time from this to this point is enough time for this thing to unlatch, it'll always unlatch. So and you have to look at that in your data sheet. If you're running at really high frequencies, if this AC is a high frequency and it's not like just your typical 60 hertz sine wave, it might not fall below the holding current long enough to actually unlatch the Triac. So you got to be careful with that. These don't work you have to make sure that your actual current flowing through your device will fall below the holding current for the specified amount of time if you want this device to unlatch. Otherwise, it's just going to stay latched once you activate it. Alright guys, so real quick, I just want to run down through the quadrants of operation of a Triac. Now this is a little bit more advanced, and a few other things I should mention. When we looked at that IV curve, you remember that there was that forward breakdown voltage, and there's also the reverse breakdown voltage, and it's kind of like the blocking voltages, right? If you go beyond that, that Triac can switch into the conducting state, as we saw. So it's really important when you're designing a circuit with these guys. First off, your loads, if they're either inductive or capacitive loads, if they're not resistive loads, you got to be very careful, because your current may not match your voltage, right? They can be phase shifted a little bit with as much as 90 degrees, and your voltages can get rather high in that case, and you can actually exceed the forward or reverse breakover voltage, and your Triac can switch into the activated state when you don't want it to. So those are just some design considerations to take into account. Also, I don't really want to get into the great depth as to why this is, but the triggering is also, the level of triggering required at this gate is different depending on what quadrant you're in. So it's easiest here, and it gets a little bit harder as you go along through the cycle, and that just has to do with how these currents are actually flowing through the actual semiconductor layers. Sometimes it's required, you have to push a little bit more current through your gate to actually open up those depletion layers in the actual junctions of the semiconductors, and it requires a little bit more gate current in different quadrants to actually trigger your Triac. So here's let's look at it. So here's quadrant 1. So this is the first 90 degrees of your cycle, right? So here is the first half, positive half of your sine wave. If we're starting here at 0, so this is 0 degrees, and 90 degrees would end right there, right? So this is your first quadrant, or your first 90 degrees. And in this case, in the on state of your triac, your gate will have a positive current and a positive voltage. And this is all relative to MT1. So if MT1 was at ground, MT2 would be our positive half of our sine wave relative to ground, right? And our gate would have a positive voltage and a positive current going through MT1. And so in this state, current would actually flow through this first half of this track, through this, we could think of it as an SCR, right? So they would flow through here. And so in this second quadrant, your gate voltage and your gate current is actually going to be negative. This is going from 90 degrees up to 180 degrees right there, where it crosses that zero again, right? And so still your current is going to be flowing this way through this SCR right here. And so yeah, and again, relative to here, so your wave coming in on MT2 is positive relative to MT1, it's ground, and your gate voltage and current is going through to MT1, and it's negative relative to the ground. And also here so this is quadrant 3, this is going to be from 180 to 270 degrees, so this is the first negative portion of your wave, and it's going to have a negative voltage on the gate to fire it. And so when you have a negative voltage and a negative current going through that gate relative to MT1, it'll fire that triac. And then the last quadrant is going to be from 270 to 360 degrees of your wave, and it is a positive gate voltage and current relative to the terminal MT1 on your triac. And what's interesting, and we'll take a look at this, is I will actually demonstrate this for you guys. I'll hook up a triac and I'll show you guys how we can, kind of like in the SCR video, we'll actually activate one, and we'll do a full wave activation where we just basically use the triac as a switch and your output will be all positive. But what I'll also do is I will hook up, I'll show you guys just kind of real quick how this is going to happen. So if I put a diode right here, our gate is only going to receive positive voltages. It can only receive positive voltages. So that means really it's only going to fire this half of this cycle, and you'll see that basically it only fires with one SCR, and it'll basically just be like an equivalent of an SCR. We'll only get our positive half of our cycle, and then if I flip this diode, we'd only get negative voltages on the other side, and you'll see that we only will get our negative half of our cycle, or our SCR. Only one of our SCRs will be basically working, because in this case, without doing any phase shifting or anything like that, we have to fire on the first half of our waveform. Alright, so I just want to show you guys real quick a circuit that we're going to build up here. Very basic. And so here we have an AC source. We'll see this is just a transformer. Here our L, this is just our resistive load, and in my case it's just a little 100 ohm wire wound resistor, and our triac is in series with that. So the load passes through terminal A1, and our actual power comes in here through A2, or the other half of our AC source. And so our gate, we're just going to go ahead and drive this through a 100 ohm resistor, and it's going to be tied up to our A2 pin. So current will flow through A2 back down, or not through A2, current will flow through the gate into A1. And so that's typically how it's done. And this is also known sometimes as MT1 or main terminal 1 and MT2 main terminal 2. So let's hook that up and let's see how it works. Also, real quick, I just want to explain something. This is just a simple way of turning it on. If we break this, it'll turn it off. So this is just basically a very simple solid-state relay, if you will. And so we're just controlling it by either connecting or disconnecting the gate pin. So it's not very advanced. There are other drivers that you can use to actually drive this with something like a microcontroller or some digital interface, where you can use just like 5 volts or 3.3 volts or whatever to actually activate this triac and turn it on, and you can get very creative with that. You can do phase control and stuff like that, but in this case we're just going to do a very simple circuit where we use this thing as a solid state relay, and we'll actually look at this waveform on the output, and I'll show you guys that it does put out a full wave as opposed to the SCR, which only gave us out a half wave. Interestingly enough, I'll show you guys this real quick. I just want to show you this. If we put a diode in here, right, this is only going to allow positive voltages and currents to flow into our gate, and consequently it will act exactly like an SCR in this case. So only one of these SCRs in our triac will latch, and it'll only give us our output will actually only contain the positive halves of our sine waves, so it'll look something like that, right? Just like an SCR. And if we flip this diode around, so if it was something like this, right, you would only get negative voltages and currents through your gates, and that would only activate the other triac, right, which would look something, well, of course it would be a different part of the wave. It would look something like this, right, and you wouldn't get your positive cycles. So that's some really poorly drawn sine waves, but you get the picture, right? So if we throw this diode in there, it's really only using half the triac, and it's basically acting sort of like a just an SCR. Alright, so I just thought I'd show you guys this real quick. We'll take a look at this in another video. This is a sort of opto-isolator. It's actually a Triac driver, so this is a part number MOC 3041, and this is a really good way to actually trigger one of these Triacs very precisely with a digital electronics or something like that. So if you want to interface a Triac to say an Arduino, you can do like web controlled AC things and stuff like that, so you can actually turn on like lights or high powered appliances through an Arduino. And not only that, because you could do that with like you could do that with a relay as well, so it's not really unique in that aspect, but you can actually do phase control with this too. So you can do light dimming, you can do motor controls, you can do all types of AC waveform controls by, doing that, chopping that AC wave up and getting out what you want, and you can do that all with an Arduino. So this is a really good chip to interface one of these Triacs with an Arduino. We'll do a whole other video on that because that's another project on its own, but it is a really cool way to interface low power with directly on the AC side. Alright guys, so very basic setup here. I just want to show you real quick how it's hooked up. It's hooked up exactly like that schematic, but I just want to show you real quick. So we have one side of our transformer leg coming out, and it's feeding straight into our load. So it's going directly into our load, and it's also being referenced to ground on our oscilloscope. So this is our oscilloscope alligator clip here, and then the other half is just running through this current meter, so we can actually monitor the current here on this meter. And it's in series, of course, coming out and running into terminal A2 or MT2 on our Triac, right? And then so MT1 is going straight to our actual load, and then the gate, and actually also MT1, so the output of the Triac is going straight to our oscilloscope as well. So that's what we're actually monitoring, the waveform coming out of the Triac on the oscilloscope. And then the gate, let me just zoom in a little bit so you guys can see this a little bit closer. The gate of our Triac is being driven through this little 100 ohm resistor, and you can see here that if I give it a little touch over here, you can see the current starts to flow through. So there's the current. So there's the leakage current right there, maybe close to 20 milliamps, so it's got quite a large leakage current, but like I said, these things are typically used in high power applications, so it's not really that large of leakage current if you want to think of it on that scale, but it is quite large. And then when we touch it, there it goes. It actually activates and goes into that conducting state, and it's acting really just like a solid state switch. So let's look at the output of this Triac on our oscilloscope and see what it looks like. Alright guys, so here it is. I'm about to actually connect the gate, so I'll just go ahead and clip it in there. And so there's the output waveform from our Triac. So I'm trying to find my marker here. Alright, so I just want to explain something. So if we look at it, it's almost like a perfect AC sine wave. I'll go ahead and put it into storage mode, and it looks pretty much perfect, right? It almost looks like a perfect sine wave, and it's really close, but there's this little blip going on here where it transitions from negative to positive, and where it crosses zero. You can see a little bit of something going on there. So let's go ahead and get a real close look at that. And actually, if you look at it, you can see that if I just shift it up a little bit to correct it, let's see. So basically, as soon as it crosses zero, it takes some time really before it actually activates. And so that's because it takes time for our waveform to actually be able to push enough current through that resistor. We have to wait I explained this really good in my SCR video. I gave you guys an actual schematic, but essentially our gate of our Triac is being driven by the AC waveform, and it's being driven through that 100 ohm resistor. So we have to wait for this AC waveform to progress so much, in this case this amount of time, before the voltage is high enough to where it can push enough current through that resistor to actually activate our Triac. So this is due to the resistance, and this is a tiny bit of actual phase control here. And I want to show you guys, if I actually bypass that resistor, so if I bypass the 100 ohm resistor, you'll see that this actually almost nearly goes away, because we're basically feeding our AC signal straight into our gate, which allows us to drive that gate current a lot faster, and it allows it to switch into the on state a lot quicker. So if I bypass that 100 ohm resistor, you'll see here that it fixes itself a little bit. It looks a little bit cleaner. So this is without the resistor, and this is with the 100 ohm resistor in series. So you can see quite a bit of a difference. It transitions a lot quicker. Still not perfect, but it's better. And it's actually more noticeable if I whack a 330 ohm in here. So if I put a 330 ohm in here, let's see what that looks like. Alright guys, so it's much more significant on the 330 ohm. You can see that that delay is quite long. And this really is how the actual phase control works, and I showed you guys this in my SCR video, and I talked about it in a little bit more detail, but we can change the resistance value in here and add delays on these waves, and this actually cuts off part of our sine wave. And if I put like a potentiometer in here, you would see, so let me actually whack a potentiometer here and I'll show you guys. Alright, so if you want a better explanation as to what's going on here, again, go back and watch my SCR video, but here we go. I'm going to show it to you guys. So I have a potentiometer in series instead of a resistor. So this is basically just a variable resistor. And so it's a trimmer pot, so I have to turn it a bunch of times. But here, the resistance is pretty much 0. So it's just going straight through the pot. And it's basically as if we just hooked it straight up before. And as I start to turn the pot, the resistance increases. And you'll see that delay before the SCR kicks in starts to get longer and longer. And so it is actually cutting out part of our waveform. If I keep going. And so basically you can use this as an actual phase control. I drew this on the board earlier, and it actually, this is how light dimmers and things like that work. And we can't go too far into it. You can see it starts to cut out and it gets all wacky. We can't go too far into it. I explained that in my SCR video, kind of why, but I'll do a whole nother video on this later on. But essentially we need to actually have our triggering a little bit out of phase with our actual line voltage, so we have to add some capacitance and stuff in there. But really, these things are not typically controlled like that, except for maybe in light dimmers. Typically they're actually monitored by a microcontroller, and you'll fire it with a pin of a microcontroller, and it has some intelligence to it. But so you can see that they're quite useful, not only as switches, but they can actually do phase control as well. Alright guys, so just like I explained earlier, if we pop that diode in series with that gate, I have the diode in there right now, forward bias, so we'll only get forward or positive voltages and currents at our gate. So I'll show you guys that right now, and you can see that it really just acts like an SCR. We're only getting the positive half of our waveform. Let me go ahead and put that in storage mode. So yeah, we're only getting the positive half of our waveform, and I'll show you guys if I flip the diode around, it will act like an SCR reverse biased. So let's look at that. And so there's the negative half of our sine wave, so it just really chops off the positive half. And again, it's just really functioning like an SCR. This is really just two SCRs, so this is one of the SCRs working, and the positive half of the wave is taking care of the other SCR, but you would have to have the other voltage or current flowing through the gate the opposite way to actually trigger that SCR. So really, this is just functioning as an SCR. Alright guys, that pretty much wraps up for this one. If you like this video, definitely give it a like and subscribe, because there's going to be a lot more material like this coming later on. I hope you guys enjoyed this one, and as always guys, have a good one.